Well, we described in some detail the relaxation, out of equilibrium relaxation of systems with disordered interactions. That was, say, the general topic. We illustrated this with a particular model that was the SSK model. We saw that there is a particular phenomenon that is aging, that besides having the property that the dynamics is non-stationary, that is standard for non-equilibrium dynamics, although not necessary. In the aging regime, there is scaling of the quantities that depend on 2 times. So that's particular of the aging phenomenon. Non-stationary dynamics, it depends on the 2 times, for 2 times correlations, 2 times responses in general. So there is this dependence on the waiting time that we talked a lot in the 2 previous days. And also there is a scaling in the long time relaxation of the system between these 2 times. So we look at this problem of the relaxation, of this slow relaxation, from 2 different perspectives, in Monday and in Tuesday. First, we defined a dissipative dynamics modeled by the Langevin equation that mimics the system in contact with a heat bath, basically. And we computed the dynamics in general, in particular the 2 times correlations for the SSK model from the Langevin dynamics, and computed the regimes, the quasi-equilibrium regimes and the aging regime, where we saw this phenomenology of time scaling. In order to get a more intuitive picture, yesterday we described how we can interpret this relaxation in terms of the landscape, of the energy landscape of the model. So the model is defined from a potential energy. So this is the landscape, the energy landscape. And we saw that this energy landscape, in particular for the SSK model, has order n critical points, stationary points. And so, for example, in our example that was to study the system after a quench to 0 temperature, so where there will be no thermal fluctuations, the system relaxes on the gradients. Say the relaxation, the dynamics is gradient descent on the landscape. So in order to relax, or the system is in a trivial landscape with only 1 minimum, probably at the ground state, or as happens in the SSK model, it relaxes going through a sequence of critical points, of which we computed yesterday the stability. The stability is a critical point of the critical points, because we saw that we can label the critical points with the n eigenvalues of the interaction matrix. And so we have a hierarchy of critical points in which there are 2 maxima, say maximally unstable. So when the system, for example, begins its relaxation from a disordered initial state, typical of high temperature, it will find a landscape with, say, dominated by saddles of high index, so with many unstable directions. So the system, we have to imagine this in an n-dimensional space. This is the difficult part of the intuitive picture, that there are not, say, 2-dimensional saddles. These are saddles with n directions. So typically there are many directions that are unstable where the eigenvalues of the Hessian are negative, and many directions which are stable. So the system has to manage to relax if no thermal fluctuations are allowed, to relax through these saddles. So this is the picture that we have to imagine during the relaxation in this particular model, that is the SSK model. So as the system goes down and down in energy, because it is relaxing at 0 temperature to the ground state, it begins to be trapped around saddles that has less and less unstable directions, because, say, the lowest lying saddle is in fact the ground state that is stable with n positive eigenvalues of the Hessian. So as the system gets trapped and trapped looking for the ground state, the time scale for relaxation grows. And this is what causes this slow relaxation, this algebraic in general and power law relaxation. The fact that the system has to find these directions in a extremely high dimensional space, because the space is n-dimensional, and we are thinking of a many-body system. So n, we think that this is very large, or going to infinity in practice. So when the number of unstable directions is few, and it's fewer and fewer as the system relaxes, it gets more and more trapped near these saddles. So this produces a kind of hierarchy of time scales, which the system has to go beyond this in order to relax. That's why, in fact, in the thermodynamic limit, the system never relaxes to the ground state, never reaches the ground state when we quench to 0 temperature. If we quench to a finite temperature, besides this relaxation through saddles, there will be activation because of thermal fluctuations. And this will introduce other time scales. But the SSK model does not hasn't local minima, so activation is not a problem, is not a question in this model. So I think that this landscape picture is what helps us to get an intuitive view of this slow relaxation. Why the relaxation is slow? It is because this trapping around or local minima, or in the case of the SSK model, around saddles with few unstable directions. And the system will flow if it finds these stable directions. But at low energy, say in the low-lying energy levels, there are few when n is large. In more complex models, or more realistic models, besides saddles, we will find local minima also in the landscape. So the landscape will be a mess, a mixture of saddles of all orders and local minima also at different energy levels. So in a particular quench, the system at some time will be surrounded by saddles and by local minima, and it has to go down if it, say, it's trying to relax to a typical state at a lower temperature. So there will typically two mechanisms. One is relaxation through saddles, as we saw happening in the SSK model, and the other mechanism is activation above energy barriers. When the saddles are more unstable, so typically at high temperatures, when the system finds saddles with many unstable directions, it is more probable to flow, say, to escape from the local region that it is exploring through the saddles, going outside, escaping through saddles, than activating through a barrier. But you see that there will be a competition between time scales. There will be a time scale for activation. is the Kramer's problem, activation through a barrier, or tunneling in a quantum system, and there will be relaxation through saddles. So these are two mechanisms in a general system, not in the SSK model that has only saddles. Again, as I try to get an intuitive view of this, at low temperatures and when the system is nearly equilibrium, the saddles will be mostly stable, say with few unstable directions, and so the time scales defined by activation and relaxation through saddles will compete. At some point, it will be more probably to activate through a barrier than to find the unstable directions of the saddles that will be few. So these are the two mechanisms for relaxation in a complex landscape, say in a system that because of disorder in the interactions that in turn produce frustration will have a huge degeneracy of local minima and critical points. Okay, so this is more or less the picture that we have in mind. Some other question for this? Okay, so let's go on. In this in the following, in this lecture, I will describe generalizations of this picture for other situations. Now we will talk a bit about what happens when interactions are non-reciprocal. In the SSK model, or in a general model where we have a potential, say, classically, Newton's third law is obeyed. So interactions are symmetrical. Our disorder matrix, the Jij matrix, was symmetrical. This, well, of course, this defines the physics of the problem in many senses. When interactions are non-reciprocal, or say the matrix of pair interactions, if there are pair interactions, is non-symmetrical or non-Hermitian, if we are studying complex situation. Say the physics will be very different. In part because we cannot define a potential energy associated. Say, when with non-reciprocal interactions, the forces are not conservative. So we cannot define a potential. And then, for example, the relaxation will not be a gradient descent on the landscape defined by the potential. So in this kind of problem, we do not have the picture of a potential through which the system is relaxing. Non-reciprocal interactions are rather common in nature, in spite that we do not study them a lot because of this, say, third law that is paradigmatic in many situations in physics. But in many systems, and probably in systems beyond physics, in biological systems, chemical systems, in active matter, there are many situations in which the interactions are non-symmetrical or are non-reciprocal. For example, in models of neural networks, when we look at the interactions between a pair of neurons, we can make a physical model of a neural network. In fact, the Nobel Prize, the last year Nobel Prize, went to two physicists that worked in the 80s in models of neural networks that now are the base of machine learning techniques and, in general, artificial intelligence. But if we think of the biological neural network, and we look at a pair of neurons, they interact between each other, and the interaction is non-reciprocal. Say, the force that one neuron exerts on a neighbor is not equal to the force that the neighbor exerts on the particular neuron. So the graph that defines the interactions between neurons in a neural network has non-reciprocal interactions, essentially. John Hopfield, that was one of the winners of the Nobel Prize in 2024. I don't know if you know the story. Basically, he proposed a spin glass model of neural network in the 80s. That is probably his most famous work. And because of the physics techniques that he knew and we are used to use in our studies, he defined the model with symmetrical interactions. So the Hopfield model of neural networks, that is very well known, in its original version, in the Hopfield's original version, has symmetric interactions. And this basically allowed to put this model in a statistical physics context, because, as I said before, with symmetrical interactions, forces are conservative. We can define a landscape, a potential energy, and eventually a Hamiltonian, and study, for example, the equilibrium statistics of the model, and also out of equilibrium dynamics, as we did for the SSK model. So this had a very strong impact in the physics community in the 80s, when John Hopfield proposed this physics-based model of neural networks. But through neural networks, both biological and artificial, have non-reciprocal interactions. So, for example, in problems of machine learning, when instead of defining a landscape and looking for the local minima that we can imagine as memories, as states with some stability in the dynamics, Hopfield thought of these local minima as memories, as a model for memory storage and recovery. In the general problem of machine learning, the problem is not to define some states that are local minima that may be interpreted as memories, but to find what are the interactions that solve some problem. We want to solve some problem by some approximation, and in the neural networks, the problem is what are the interactions that solve the problem. This is the basic, say, qualitative question in machine learning. So, well, this is one of the motivations of looking at non-reciprocal interactions. In many other systems, even in quantum systems, there is a rather big area called non-Hermitian quantum mechanics, in which systems with non-reciprocal interactions are present. For example, when systems are studied in contact with an environment, and the system does not react to the environment in the same way as the effect that it suffers from the environment, the interactions are non-reciprocal. And so that can be taken into account, and the description of the physics of this problem will be very different as when we have reciprocal interactions. Here I will I will not speak about any of these particular situations, but I will follow the line that we have talked about in Monday and Tuesday. So in principle, if we relax the condition of symmetry between the interactions, we would like to answer some basic questions. For example, what happens with the slow dynamics? This is the same qualitatively, the relaxation of the system, when we allow, for example, for a small degree of asymmetry between the interactions. How does the relaxation proceed? It is similar, say, the picture of relaxation besides the fact, or in spite of the fact that we have no potential energy that can be defined. But the Langevin relaxation, for example, of the system is similar or not? What happens to the aging, for example? And in general, what new features we can expect when interactions are non-reciprocal? What are the changes in the dynamics? And we will see in the end that if we look again at the stationary points of the dynamics, as we did for the SSK model, we will have some surprises, mainly if we are able to compute the number of stationary points. Remember that in the SSK model, the number of stationary points is exactly 2n, so an extensive number of stationary points. And as we described, the presence of the existence of these stationary points and their stability is critical for the kind of relaxation that we see. In the case where the interactions are non-reciprocal, the number of stationary points scales in a different way with n. And we will see that this produces qualitative changes in the dynamics, in the relaxation. So in the first part, we will study again the Langevin dynamics at 0 temperature of the model by relaxing the condition of reciprocal interactions, by allowing a certain degree of asymmetry, of non-reciprocity in the interaction matrix. And then at the end, we will interpret again what we see in the relaxation of two-time quantities from a landscape point of view. But remembering that in this case, we won't have a landscape. We won't have a potential energy because forces are non-conservative. So we have to interpret the effect of the stationary points in a purely dynamical way. There is no, say, static picture of the static picture of the landscape. Okay, this is the motivation. So, bit formally, what happens when we allow for a certain degree of asymmetry between the elements of the coupling matrix? For example, let's define the Langevin dynamics at 0 temperature. It is the same set of equations as in the symmetric case, but now the couplings have some degree of asymmetry that is characterized by this parameter eta that can vary between -1 and 1. Eta equals 1 is the symmetric limit. When eta equals 1, say the variance of the couplings that are random variables scales as 1/m. This, as we said before, is in order to have an extensive limit when n goes to infinity, because this is a completely connected model. But now, instead of having complete symmetry, in which case eta would equal 1, and it will be equal to jij squared, we allow for some degree of asymmetry between -1 and 1. Eta equals 0 means completely independent entries. So we will describe again this disordered matrix as having real Gaussian entries. So all the elements of jij are picked from a Gaussian distribution with this variance and these correlations. And for example, what will be very different from the symmetric case is that the eigenvalues will be complex. So the ensemble that describe this kind of random matrix with asymmetric entries is a different ensemble. It's not the Gaussian orthogonal ensemble that we saw in the case of symmetry, but it is this real Gaussian elliptic ensemble in which for a general eta, the distribution of eigenvalues is in the complex plane. Eigenvalues will be complex, so they will have a real part and an imaginary part. And for general eta, they will be distributed in, say, for large n inside an ellipse. So here there are, we can see 4 examples for eta equals -0.5 at the left. So the ellipse is elongated mainly on the imaginary axis. When eta is negative, correlations are antisymmetric, so the entries are antisymmetric, tend to be antisymmetric. For eta equals -1, they are completely antisymmetric. Okay, jij is equal to -jjy when eta is -1. In this case, all the distribution will be on the imaginary axis. But for general eta, we will have typically an ellipse. For eta equals 0, the distribution is a circle when the entries are independent. Say jij picked independently of jjy. So a matrix with Gaussian elements, but independent. This will be the case of eta equals 0, and the distribution in the complex plane is defined by a circle in that case. When eta is positive, is larger than 0, but less than 1, we will have an ellipse elongated along the real axis. And of course, as we have seen, when eta is 1, it is the case of the symmetric matrix, and the distribution of eigenvalues lies in the real axis. When the matrix is symmetric, the eigenvalues are real. But when it is asymmetric, the eigenvalues are complex. And the ensemble that describes the statistics is this, well, in the case that the entries are real, because the elements of the matrix may be complex also. But we will work with real elements, so this is described by the real Gaussian elliptic ensemble. This is another ensemble, so the statistical properties of the eigenvalues are completely different in principle than, for example, the eigenvalues that we described from the Gaussian orthogonal ensemble in the case of symmetric interactions. So you see that basically because of this behavior of the statistics of the disorder matrix, we can expect a completely different dynamics for this system, excuse me. A completely different dynamics, because we, for example, can expect oscillations that were not present in the symmetric case because of the imaginary part of the eigenvalues.
A clarifying question. So in the previous case of the orthogonal ensemble, we were only we're sampling to get the, let's say, the upper triangular part of the matrix and then forcing it to be symmetric. In this
Yes.
case, we're sampling every single
Exactly.
element, both upper and lower triangular, but it's these correlations that make it either like on average orthogonal or not, you know? So is that correct?
Yeah, that's correct.
Okay.
Yeah, that's exactly the situation. Say you sample all the elements, not only the upper triangular, but you sample them obeying these definitions. So there are some degree of correlation defined by it. Exactly. That is. So when you do that and you diagonalize the matrix, you will see that the eigenvalues are complex generically and are distributed inside an ellipse. Okay, so this is the situation a priori. So let's go to the, before going to the dynamics, the fact that the matrix is asymmetric or in general non-Hermitian changes things a lot. One thing is that the eigenvalues will be complex in general with asymmetric or non-Hermitian matrices, as we described in the previous slide. But they are also we will have to define right and left eigenvectors. So in an asymmetric matrix, there is not an orthogonal transformation that diagonalizes the matrix, but there are right and left eigenvectors with the same eigenvalues. So the distribution of eigenvalues, or the eigenvalues of the matrix, are the same, but if we act on the right or on the left, there will be different sets of eigenvectors, right and left eigenvectors. This existence of right and left eigenvectors, that in the case of a symmetric matrix, they are the same. There is only, say, right and left, if we want, are the same in a symmetric matrix, will also play a crucial role in the physical properties of the system. Say, we could prove that right and left eigenvectors form a B-orthogonal set, so they are orthogonal, but they are not orthogonal within each subset. So right eigenvectors are not orthogonal between them, and left eigenvectors are not orthogonal between them. They are orthogonal to an eigenvector of the other kind, so left and right eigenvectors. This will be important in general in the physical properties. We will describe the effect on the dynamics, but in general in the physical properties, the fact that the eigenvectors are not orthogonal within each subset, right and left, has strong implications. And also, well, they obey a completeness relation, right and left eigenvectors. Okay. So in order to try to solve or to study the dynamics, here we have changed it a bit, the notation. We have defined the state vector with the bra, say that is, as always, this vector with the n components of the dynamical variables of these generalized spins. H is an external field, as usual. We can define the projections, this small r, the projections of the state vector onto the right and onto the left eigenvectors. So now we have somehow duplicated the number of quantities that we have to take care about. So when we apply in the basic dynamical equation right or the left eigenvectors, we will have two sets of equations. One, for example, for the projections onto the right eigenvectors, and another set, say one set, these are n equations, and another n equations for the projections onto the left eigenvectors. Now, let's look a bit at the form of these equations, remembering the equations for the symmetric case. We will always have the symmetric case as our reference, because in principle we want to see what is different in this case if we relax this hermiticity property. Well, these equations, if we come back, is similar, it is basically the same than the equation in the basis that diagonalizes the disordered matrix as we had in the symmetric case. The eigenvalues, the Lagrange multiplier, and an external field term. That this is the projection of the external field onto the right eigenvector. Now we will also have to take care if we are projecting onto the right eigenvectors or onto the left eigenvectors. So they are two separate sets with separate properties. So we will have to project onto both. And, well, say an immediate consequence is that we will have a duplication of the equations, say, of the dynamical equation. But this equation is the same as before. The different equation is the set of equations for the left projections, for the projections to the left eigenvectors. So we have the term corresponding to the Lagrange multiplier that is basically the same, but here we have a sum, and see that we have this matrix, these elements that come from the left eigenvectors, and a coupling to the right eigenvectors. So in this equation, there is a coupling between right and left eigenvectors. In the symmetric case, there was only one kind of eigenvectors, and they were orthogonal between each other because of the orthogonal transformation that allows to diagonalize the matrix. So in the case of a symmetric matrix, this set of eigenvectors would be orthogonal. So this would be a Kronecker delta function. And then when we sum with a Kronecker delta function, if they would be orthogonal, we will end with the same equation as for the right eigenvectors, saying that in that case, if they would be orthogonal, the equations for the right and for the left would be the same. So conclusion is that when they are orthogonal, we have only one set of equations. That was the situation in the symmetric case. But now we have said that left eigenvectors are not orthogonal between each other. So this is important because this changes the dynamics. This introduces this term that is not non-trivial. It is not simply a delta function here. The same happens between correlations between right eigenvectors. They are not orthogonal. Okay, so we have to solve the two sets of equations. There is some degree of correlation between left and right eigenvectors. Basically, we can proceed as in the symmetric case. Say, we will not get into the calculations because now are more cumbersome, are more complex, but again, for the SSK model, so we are looking at the dynamics of the SSK model with non-reciprocal interactions. So we are looking at the new ingredients of the model when non-reciprocal interactions are present. Say, the technique for solving is basically the same. We can go through the same steps that we did for the symmetric case. But the calculation is longer and it's a bit more complex. In the end, if we do that, we can obtain for disorder or random initial conditions, the same as we studied in the symmetric case. We can arrive at expressions for the 2 times correlations and the 2 times responses that depend on a function that is this W function that it turns out that is defined in this way. It depends on these internal products between left and between right eigenvectors. Again, remembering the case in the symmetric case, in which case these brackets would be equal to Kronecker deltas because they would be orthogonal. If they would be orthogonal, the eigenvalues would be the same. So this would be a sum over only one index. The eigenvalues would be real. So this is the complex conjugate of lambda beta. But in the case of orthogonality, we are back in the symmetric case, and the eigenvalues were real. So the expression is simpler in the symmetric case. We would only have a single sum of an exponential and nothing here. And we saw that in the previous lectures. If you goes back and see the expressions, we called this W function gamma in the case of the symmetric, a gamma function in the case of the symmetric model. And the computation was simple because in the thermodynamic limit, this sum turns an integral over the density of eigenvalues, remember? And that integral, we saw that it's exactly solvable in the symmetric case. The integral of the density of eigenvalue, that was the Wigner semicircle law, plus the exponential, was exactly solvable. And from that, we solved the dynamics exactly. Now, it is a bit more difficult to solve this because we have no Wigner semicircle law. We are in a different ensemble, that is this elliptic ensemble. And we have the problem of having to deal with the eigenvectors besides the eigenvalues. In the case of the symmetric problem, that is not particular to the SSK model in general with symmetric interactions, all was dependent only on the eigenvalues of the disordered matrix. So if we knew the statistical properties of the ensemble of the eigenvalues, plus the thermal noise and plus initial conditions, the dynamics is defined. Depends only on the distribution of eigenvalues. Here, with non-reciprocal interactions, we have to look and to compute things not only dependent on eigenvalues, but also on eigenvectors. So we have 2 sets of eigenvectors, left and right, and all things depend also on the eigenvectors. This is different from the case of the symmetric case and makes things more difficult. Okay, after all this, in the case of the SSK model with non-reciprocal interactions, this can be computed. So we can compute this exactly. So now let's look at some results. If we compute from the previous expressions, we will focus on the correlations. So we have to compute this function. This is the 2 times W function that is defined here. So in order to get those results that are valid in the thermodynamic limits, say for large n, we have to do this large n limit here. This will lead to an integral with some quantity that is a kind of matrix of overlaps between eigenvectors. So there is a technique to solve this problem that is known. And if we do that, we compute the 2 times W quantity, and in the denominator we have the 1 time W, so when times are equal, we compute this, and we get expressions for the 2 times correlation function, and we can analyze the different regimes, the different time regimes, as we did in the symmetric case. So we can look if there is a quasi-equilibrium regime, there is some stationary regime, say, and we want to look particularly if there is an aging regime, a regime in which the dynamics is non-stationary, and if there is scaling between the 2 times. That is the defining feature of the aging regime. Again, remember that now we haven't a potential energy, we haven't a landscape picture, because the forces are non-reciprocal, so they are non-conservative. So that, besides several points, means that we cannot have a Boltzmann equilibrium for the system. We cannot define, say, the thermodynamics or an equilibrium statistical mechanics, because there is no Hamiltonian for these systems with non-reciprocal interactions. So this is completely different from the previous case. So the dynamics, we can write the Langevin dynamics, interpret it, but it is a purely dynamical system. We are analyzing a purely dynamical system. Okay? So these are some results for the 2-point correlation functions. In the case that the asymmetry of the interactions is positive, is between 0 and 1. Remember that 1 is the symmetric case. Eta equal 1 recovers the symmetric case. Eta equals 0 means that Jij and Jjy are completely independent. We sample them independently from a Gaussian distribution. In the left panel, the value of the asymmetry is fixed, in this case to 0.7, and we plotted different curves for different waiting times. So what appears, say at first sight, is that for different waiting times, the relaxation is again non-stationary, so the curves depend on the waiting time, as was the case in the symmetric model. But, well, there is a plateau that, because we are working at 0 temperature, it is fixed at 1, at correlation equal 1. And then after some time, the plateau gets longer the larger the waiting time. That is similar to the case of the Asian regime in the symmetric case. But the final relaxation does not present scaling. It is exponentially fast. It is not a power law. So this is a difference that from the symmetric case that is induced by this asymmetry in the interactions. If we compute the correlation function in the regime in which both times, in this case, the waiting time and tau, that is the difference between t and the waiting time, remember, in the case in which both times are large, but the relation between them is a small fixed number, so they define a scale. That was the aging regime in the symmetric case. We do not find power loss. We find instead an exponential relaxation. See that, well, of course, all this depends on the degree of asymmetry. There is a power law, but it is a prefactor of an exponential. And the dominant term here, this is small. This is small because T weighting over tau is small. So the dominant term at large taus is the first. So it is an exponential decay. It is an exponential decay with a rate that depends on the degree of asymmetry. Okay? So this is the picture. So this is what appears to be this equation. So what is the conclusion? Well, the dynamics is non-stationary. It is, of course, a non-equilibrium dynamics, but aging is destroyed somehow. We say T and T weighting do not show scaling behavior. Say the correlation does not depend exclusively on T weighting over tau, as was the case in the symmetric case. So we cannot collapse, for example. We cannot produce a collapsing graph because there is no scaling. There is this tau that dominates the relaxation at the long times. When eta goes to 1, when we make the model more and more symmetric, say the matrix more and more symmetric, when eta goes to 1, this rate goes to 0, basically, so the time scale of the exponential relaxation diverges. So this is a breakdown of this exponential relaxation. With eta equals 1, we recover the symmetric case, in which case we saw that the relaxation was VI power law, and there was scaling in T weighting and tau. This can be seen in the plot on the right side that corresponds to a particular T weighting, in this case, 40, and different values of the asymmetry of the disordered matrix. So we can see that for growing symmetry, the time scale of the exponential relaxation grows until for eta equals 1, in which case we recover the symmetric case, the relaxation turns to a power law. So this is captured by this expression. So the dynamics keeps some features of the aging phenomenology, but not all, and mainly it loses the scaling between the times. So it is a non-stationary dynamics, but without aging. We would not say that this is an aging dynamics. Okay. Now, let's see what happens when the entries of the matrix are anticorrelated, have some degree of anticorrelation. So when eta is between -1 and 0. Again, remember, eta equals 0 means that Jij and Jy are completely independent. So the highest degree of asymmetry. And -1, they are exactly anticorrelated. One is minus the other. In this case, we see here are plots of the absolute value of the correlation, because we will have oscillations in the case in which the Gaussian entries of the matrix have some degree of anticorrelation. In fact, well, this depends on the value of eta. For eta equals -1, in which the entries are exactly anticorrelated, the dynamics at the long times is stationary. So this is, again, a different behavior compared to the previous one, in which eta was positive, and compared to the case of symmetric interactions. So if interactions are perfectly antisymmetric, correlations and also responses, if we compute them at the long times, are dependent only on tau. This is a Bessel function, and they depend only on the difference between the largest and the waiting time, on tau. So it is a time translation invariant dynamics. The Bessel function at large arguments shows an oscillation that is damped by a power law. So this is what we can see, not here, but here for eta equals -1. That is the black curve. So the behavior is given by this cosine, by an oscillation, and is damped with tau to the 3 halves with the power law. That we will see it is different from the behavior for other values of eta, that we will also have an oscillation but damped exponentially. But in the case, in this extreme case with antisymmetric elements, the relaxation, the damping is given by power law. Again, like in the previous cases, if we fix eta here in the left side, eta equals -0.8 and different waiting times, we see again this dependence on the waiting time. So the dynamics is non-stationary in general, except in this limiting case of eta equals -1. And there is the plateau, and there is some time scale that can be computed. It is a particular time in which, in the calculation, there is a square root that turns to be negative inside, and so the result changes from a real result to a complex result, and so oscillations appear. So for any t waiting, there is some tau star from which the system begins to oscillate. In the right, we fix t waiting, in this case 5, small t waiting, and we see curves for different values of the asymmetry. Well, and we will see that when the asymmetry is different from -1, it will show also oscillations, but exponentially damped. So it is possible to compute exactly this value of tau star. It depends on the degree of asymmetry and on t waiting, after which oscillations appear. This is a strange thing. Say the relaxation is monotonous, say, does not oscillate until a particular time from which the relaxation, say the dynamical behavior shows oscillations. If we compute the 2 times quantity, we obtain basically this result, an oscillation, a cosine that depends again on tau, on t waiting, and on the degree of asymmetry, but damped by an exponential. This is what we saw in the previous figure. And in general, for eta different from -1 and different from 1, the results depend on both times, on tau and on t waiting. So there is no time translation invariance except in the extreme situation of eta equals -1. Okay, so this is basically the changes in the phenomenology of the relaxation when we introduce some degree of asymmetry or of non-reciprocity in the interactions. Well, here we are working with a particular model, again, with the SSK model, with non-reciprocal interactions, but this is a general feature of dynamics with non-reciprocal interactions. This is these oscillations that were not present in the symmetric case. So oscillations appear. We can say interpret the appearance of the oscillations as a consequence of the complex eigenvalues, the fact that the eigenvalues have an imaginary part besides the real part. In the symmetric case, eigenvalues are real. So we didn't expect oscillations in that case. But here, the distribution of eigenvalues is in the complex plane. So this is basically the reason why oscillations appear. And we can characterize this in detail for this kind of model. A general conclusion, comparing again this asymmetric case with a symmetric case, is that the dynamics is faster in this case. The phenomenology is similar. There is a plateau in the 2 times quantities and then a decay, a final relaxation. But the relaxation in this case with asymmetry is exponential, is exponentially dominated. And in the symmetric case, it was given by power laws. So the dynamics is fast in this case. So again, comparing and using the symmetric problem or the symmetric case as a reference, we can ask, can we interpret this faster relaxation in terms of stationary points of dynamics? We saw that in the symmetric case, stationary points of the landscape, in that case, were very important. Say we are able to interpret the relaxation by looking at the number and the stability of the critical points in the symmetric case. Here, we can compute the stationary points of the dynamics. They will not be critical points of a landscape because we haven't the landscape in this case. But we can compute the number of stationary points. And if we do that, it turns out that the number in this case is much smaller than in the case with symmetric interactions. Say, we can go basically through the same kind of calculation in order to compute the stationary points. So we write again the dynamic equation, diagonalize, and say project onto the basis that diagonalizes the disordered matrix, and we end, as we saw, with 2 kinds of equations, one which come from the projections onto the right eigenvectors, another that comes from the projections onto the left eigenvectors. And this more simple equation has an important interpretation for this question of what happens with the stationary points. We can solve this as we did in the symmetric case. Say there is a trivial solution for this for the projections onto the right eigenvectors, in which these are 0, but these are not relevant or valid for this model with a spherical constraint. So we have to look at cases in which the Lagrange multiplier equals 1 of the eigenvalues. If it equals 1 of the eigenvalues, it will be different from the others. So from there, we can conclude what are the values of these projections. But besides that at a critical point, at the stationary points, the Lagrange multiplier equals 1 of the eigenvalues. It is simple to see that the Lagrange multiplier is a real quantity, even in this case. It is not a complex function, for example. It is real, because we can compute it from the stationarity condition simply from here, and look that and realize that Z is equal to this quantity, to this element of the J matrix, when we act with the state vector from the right. And you see that the state vector, the original state vector S, and the matrix are real quantities. The matrix has real entries. So Z is real. Z is a real quantity. If Z is a real quantity, and at the stationary point, it equals 1 eigenvalue, the eigenvalue has to be real. So the eigenvalues that are associated to stationary points are not the whole n eigenvalues of the matrix that are complex in general, but only the real eigenvalues, the eigenvalues that lie on the real axis. And these are much less in number than n, that is the total number of eigenvalues of the matrix, that is n plus n matrix. So this is an important conclusion. Z is real because J and S are real, and it has to be equal to some eigenvalue in order to satisfy the stationarity equation, this stationarity equation. So the eigenvalue in that case must be real. Well, there is a known result in random matrix theory for this ensemble, for this real elliptic ensemble, for the number of the scaling with n of the number of real eigenvalues, on the real axis, and it turns out that they scale with square root of n. So the number of real eigenvalues goes with n as square root of n, that is much less than n. So what is the conclusion? And so at the stationary points are in a one-to-one correspondence only with real eigenvalue. This is, say, a priori the conclusion. And they are much less in number than the n eigenvalues in the complex plane. So comparing to the symmetric case, in which we had n stationary points, that in that case were also critical points of the landscape, here we have square root of n typically stationary points. So a less number of stationary points. This may be, say, the origin of this faster relaxation, that as the system relaxes, it finds a much fewer number of stationary points that work against the relaxation in some sense. So the picture is simpler from this point of view than in the symmetric case. The system will flow through stationary points, again, here in a purely dynamical situation. It is a dynamical system with n degrees of freedom, so in large dimensions. So it is a complex dynamical system. And there are a lot of stationary points. The system will flow near these stationary points through the stable directions and will flow out of the stationary points through the unstable directions. That because we are in a high dimensional space, there are many stable and many unstable directions, as we saw again. But there are fewer stationary points than in the symmetric case. So this is at the origin of this faster relaxation, exponential relaxation, compared to the symmetric case. Of course, we should look now at the stability of the stationary points. Here we look, say, a bit only at what are the stationary points. What is the number of the stationary points? We should look at the stability. This has not been done up to now. We are working on that. But only from the number we can anticipate that probably this is at the origin of this faster dynamics. Okay. I think that this is a good point to stop from now. So, if there are questions? Yes.
But there's still this plateau, right?
Yes.
Isn't it? I understood it before more that this is the main characteristic of aging, because physically it's like a quasi-equilibrium regime. Like, So, but now you're saying aging is like really related to this power law decay or of the correlations, but why do we care so much about this, how it's decaying if we have this plateau which gets longer and longer?
Okay. There is no, say, a formal definition of aging. There's no definition of what is aging. But in general, it is associated to these two characteristics, the existence of a plateau and then the existence of a long-time relaxation that is governed by power laws and by scaling between the two times. So both ingredients are important. The plateau, that is, say that the system as it goes down in the landscape, say in the symmetric case, it gets trapped in a restricted region of phase space. So this generates the plateau. It finds difficult to decorrelate. So this is part of the phenomenology of the aging regime. But in order for the relaxation to be called of aging, you need also a long-time relaxation in which there are scaling between the time scales. In this case, we are looking at two time scales, at two time quantities. So we saw in the symmetric case that the two times correlations and also the responses depend only on tau over T weighting, only on this scaling variable. So the scaling is part of the definition of aging, not only the quasi-equilibrium regime. In this case, there is no scaling between tau and T weighting. There is the plateau, as you said, yeah? So, okay, there is some trapping of the dynamics from some time that may be large. The system wanders around a limited region, so correlations stay at a high value, but then relax. And in this case, with non-reciprocal interactions, the relaxation is exponential. So when it manages to go out of this trapping, it relaxes exponentially fast. So in this sense, we say that this is not an aging behavior. But as I said, aging is not a mathematical definition. But in general, what say in the community we mean by aging is the presence of these two characteristics, quasi-equilibrium regime followed by a relaxation with scaling in the two times.
But let's say there's an experiment done, and as long as you're in the plateau, there's no way to distinguish whether you have this one phenomenon or the other.
If you stay at time scales in which the system stays on the plateau, there is no way to distinguish. Yeah, the dynamics is stationary in that case. So in fact, this is a problem with these disorder systems, that the plateau may last time scales longer than any, for example, characteristic time scale of the laboratory. If you are looking at these quantities in the laboratory, you look from a certain time scale. And in this kind of systems, maybe that the relaxation gets stuck in the quasi-equilibrium regime from during the time scale you are looking at. And you can think that the system is in equilibrium, but in fact it is not. It is in a quasi-equilibrium regime given by this trapping of the dynamics in a restricted region. So this is difficult to say, to disentangle in practice, if the system is in equilibrium or not, by looking at these quantities. Of course, you can compute other things that tells you if the system may be in equilibrium or not. But the quasi-equilibrium regime, it's a quasi-equilibrium regime. Say, dynamically, it's stationary. So you may think, well, the system equilibrated. I wait, say, a day or a week in the laboratory, and the system has already relaxed. But if you do that in a glass, for example, you will see that if you wait long enough, at some time it will relax further. and it will go to this aging regime. So there is a question of time scales. Say equilibrium in this kind of systems is difficult to confirm, say, experimentally, in practice, even in a simulation. When you do a simulation, you will have these growing time scales as the system, for example, is quenched to a low temperature. And maybe in the times that are accessible to the simulation, you only see the plateau, the quasi-equilibrium regime. But that's because the time that are available for the simulations are not enough to let the system relax. If you think of this situation as caused by frustration, for example, by geometrical frustration that is present, say, in many systems, but particularly in glasses, a problem is that in order to see a fluctuation that allows the system to go out of this plateau and relax, these fluctuations involves a rearrangement of different sectors of the configuration of the system that are very costly in energetically. So if you think that you need an activation process in order to relax, at the low temperatures, activation costs a lot. Say, the time scale of activation is very long. So in frustrated systems, this is what happens. You have to make a move of many sectors. It's like a puzzle. You have to move to simultaneously many sectors. By local moves, you won't be able to find or to reach a completely different configuration that allows you to relax. So you can see this from different points of view. Say, the time scales, the landscape picture, or in this case, say the number of stationary points. You can look at from different points of view. But this is the difficulty with these systems in order to be sure if it reached equilibrium or not. Time scales are important. So we can say that, okay, this is the situation at this time scale, at the time scale that I can look and measure. But I don't know what happens if I wait longer.
The results you showed for the non-reciprocal model, they're all at 0 temperature.
From there?
For the non-reciprocal, 0 temperature.
Yeah, 0 temperature.
If we include temperature, I mean, we're not relaxing towards a thermal state because it's non-reciprocal. So can we say anything about the eventual ground state that the system is going to?
No, because, well, ground state, so in the case of non-reciprocal interaction, we haven't Hamiltonian, say there's no energy. So, well, what is the ground state? It is the stable, the dynamically stable state with the highest degree of stability. So it is a fixed point of the dynamics in which all directions, say in this high-dimensional space, are stable. So it is a stable fixed point. That's the ground state. But we have to interpret this in a dynamical way, so from dynamical perspective, because there is no Hamiltonian. So we think it will flow to a stable critical point of the dynamical system.
I'll ask another question. So experimentally, it might be very hard to see, as you mentioned, the eventual decay out of the plateau. Is it possible to see it in experiments? Like I imagine, like in a glass, once it's like heated up and you quench it, I guess you would have to start the measurement very quickly after that. So my question is, what can be seen experimentally and what are the difficulties?
Yeah, you can do experiments in order to test all this. It depends on the final temperature, on the temperature of the bath. Now we are doing the extreme experiment of quenching to 0 temperature, so extracting all, say, kinetic energy instantaneously. But if you quench to a low but not so low temperature, you will have thermal fluctuations. And with thermal fluctuations, you can cross barriers through thermal fluctuations. So in a glass or in a glassy system in general, the phenomenology, say to test this phenomenology, you need to know where is the glass transition. In general, there will be some temperature at which you will find the glass transition. In general, for temperatures below the glass transition temperature, the system freezes, and so the window glass becomes solid and freezes, and dynamics in practice freezes for, say, astronomical time scales. We can see the glass, say, 100 years, 1,000 years, and nothing will happen. But instead of that, structurally, say, microscopically, it is not in absolute equilibrium state. So that's the point with time scales. So in practical time scales, it is in equilibrium. If we measure any quantity in the glass, it is like solid in equilibrium. But if we look at the theory, say at the microscopic theory, and we interpret this in the perspective that microscopically it is an amorphous system, there is no, for example, crystalline lattice, immediately we can conclude that, well, relaxation will be frustrated, will be influenced by this frustration, and probably many long time scales will appear. Say in the lab, you prepare the glass in the liquid states, say at high temperature, and you can quench. And as I said, if you know where is the glass transition temperature, well, you can quench near this transition temperature and control the dynamics in that sense. Say above, the dynamics will be fast. Below, it will be slow. And it depends on the temperature, because temperature will induce thermal fluctuations. Other questions or comments? Okay, so let's go to the coffee break. Thank you.